did our project on Asian options, myself, Will, Theo, Snowhall, and Vaikunt. So to start it off, I'll just be running you through a brief introduction into some of the basic attributes of an Asian option. So an Asian option is an exotic derivative where the payoff is determined by the average price of the underlying asset over its maturity. So it is a path-dependent contract. The payoff of an Asian call would be the strike price minus the average asset price over its maturity, while a puts payout would be the underlying asset price is average subtracted by the strike price. And so the average of the asset price can be calculated arithmetically or geometrically. To properly price an arithmetic Asian option, you would need to use numerical methods such as a Monte Carlo, as we did in our project, which is unfortunate because a nice closed form solution exists for a geometrically average Asian option. So as an exotic option, Asian options can get, there's a lot of different stipulations that can be made within the contract, one of which would be averaging in style versus averaging out of style. Averaging in style is much more common, and it samples at discrete and regular time intervals, so weekly, monthly, quarterly, or annually averaging from inception to maturity date. Conversely, averaging out of style would be sampled near to the maturity date, which is typically more risky. So I mentioned earlier that geometric Asian options do have a closed form solution. That's because it follows a log normal distribution, which is very similar to the Black-Scholes formula. Whereas that does not exist for an arithmetic Asian option. Furthermore, so due to the averaging mechanic of an Asian option, its volatility is much lower than that of a regular option. So for that reason, it is favored by a lot of people who might be exposed to rapid changes in asset price, and it allows them to hedge their risk. So therefore, an Asian option has a lower price than a European option. So to give an example, consider an airline that steadily buys crude oil whose supply price is not fixed, but set weekly from a particular benchmark. The airline may hedge themselves against a spike in oil prices by using a tailored Asian option to reflect the weekly purchases. This would be less expensive and more convenient than buying a basket of European options expiring at weekly intervals. Asian options are also useful in markets with low volume, as the derivative would protect against price manipulation of the underlying asset. So that covers just the basic attributes of an Asian option, and I'm going to hand it off to Theo to talk about a little more about our numerical methods towards pricing it.
Maybe you can expand this further, make it a little bit bigger.
Yep.
Yeah, better. Yeah. Thank you.
Yeah. So a few words. Hi everyone. I'm Theo, and I'm going to briefly go through some of the methods that we use to price the arithmetic Asian option, some of the assumptions we made, and some of the techniques that we used in order to mitigate the consequences of those assumptions. So as a base, we used the geometric Brownian motion, a stochastic process that would model our price paths across time. And we decided to use a Monte Carlo simulator in order to price the arithmetic Asian option. There is a variety of different techniques out there, and as Will said, it is unfortunate that there is no closed form formula, and it's especially more troublesome when it comes to what the industry actually uses, which is arithmetic Asian options. So it just becomes an imperative to solve the arithmetic averaging and use the geometric averaging Asian option as a control, since it has a closed form solution and can provide us with a benchmark that we can use to estimate the accuracy of our model. So some details on the way we generated the geometric Brownian motion. We decided to push the limits of computation and try to get to extract as many paths as possible and generate them in the shortest amount possible, in the shortest amount of time possible, so that we can generate an as accurate as possible arithmetic average and an equivalent geometric average, and then just evaluate those results with this and other techniques that we use to reduce the variance of the final results. In terms of the geometric Brownian motion, we decided to get away from iterative processes, which take a lot of time computationally, and we decided to go for vectorized approaches. We used Google's Compute Cloud to generate a lot of paths, and then take the averages, take the arithmetic averages, as well as the cumulative products and the reductions to the products of the price paths. This is a small example of, or it is a subset of it's a proof of concept essentially of the path generator. This is only 1,000 price paths with 10,000 time steps and an initial underlying price of $100. The averages for the arithmetic average, or the general numbers that we used for that, was in the range of 100,000 to 1 million paths, and time steps of 100,000 to 1 million as well. And these generated paths were essentially the base for the arithmetic pricing model that we developed. We use, our fundamental assumption is that the arithmetic average follows a log normal distribution, which again doesn't come very easily, and it's a fairly large assumption to make, since we don't know what the exact distribution is, but it so happens that we know that for the geometric average, the distribution is log normal. And we decide to take the same approach and derive the Black-Scholes Merton formulas based on that. So this enables us to just simply assume that the Asian option is a European option, but has volatility of a factor of square root of 3 less than that of a European. We decided to calculate a lot of, we decided to take this time-wise approach a little bit further and calculate the Greeks across all different time steps of the averages of all of the different paths that we made, in order to reduce the variance and the standard error of our estimators right off the start, without the need of any variance reduction models, which we realized was, it was one step, but the geometric averages and the arithmetic averages just have inherent standard errors embedded in them. So that made the need for a variance reduction technique necessary. So here, you can see the method, the specific method that we used. Apologies for the raw code. This was supposed to be pseudocode, but it would just take a lot of different pages for no reason. But it essentially calculates all of the different derivatives across all different time steps. Using those, we can estimate the accuracy of our model further, since we have a closed form formula for the geometric average, and which could readily be used to compare these Greeks values with them and just measure the accuracy of the model itself. With regards to testing, these are a few of the experiments that we made. We decided to price the geometric Monte Carlo definition of our pricer with the Black-Scholes Merton model, which again did not need any variance reduction. It is pretty straightforward here. The errors were just really small right off the start again, all of them with less than 1%. So this one was a promising result, but again, it doesn't necessarily apply for the arithmetic average. So we decided to deploy, again, these variance reduction techniques that I mentioned earlier, and more specifically, the control variates method that we also discussed in class. So in short, with the controlled variates technique, we calculate the price of an option using our Monte Carlo pricer, and we calculate the equivalent numbers of geometric Asian options and their average. And we subtract the geometric average from the arithmetic average. And that difference is what makes the control variates method work very efficiently. That difference essentially gets appended to the arithmetic price at the end of the procedure, and that gives us an adjusted arithmetic average, which is closer to the true price. With regards to the specific numbers of simulations and paths that we used, we took the very simple fact that the standard error of the estimator, as you can see here, the sigma factor, is scaled, or I guess is reduced by a factor of square root of n. So given that we had a lot of computational power and that we could generate a lot of paths by just increasing that factor easily without the need for, without any concerns for computational complexity, we decided to increase the sample size by a factor of 1,000 for the original sample, which led us to the 1 million mark for the steps and the paths that we generated. And for the model that used the variance reduction technique, it is slightly more complicated. And to our surprise, we really pushed the computer to its limits. And we could only increase it by a factor of 100. But again, as we saw, this is enough to just reduce the standard error of the sample of the estimator by a factor of 10. Specifically with regards to the hedging analysis, we thought that this would be an interesting way to see, to test some of the facts of financial theory, test some of the fundamentals of financial theory, and specifically the delta hedged portfolio, which essentially says that once you calculate the delta and you just account for that in your options portfolio, then at the very end of the portfolio's life, you will end up with at least the amount that was originally set in place. So that makes it very appealing for investors, and in any kind of times, turbulent times like this, a delta hedged portfolio, if not more with regards to the order of Greeks, is essential to manage all of the risk that it entails. This reduction occurs with this simple expression, which is essentially the call option of the call price of the options at time t, reduced by the delta times the spot price of the underlying instrument at the same time, gives us the delta hedged portfolio. And further down, we also have some of the results that we extracted, some of the preliminary results, which just show very roughly that the variance and the variability specifically of the options prices in the hedged portfolio is greatly reduced. It was reduced by a factor of 2, in fact. So we just slashed it in half just by accounting for that very simple fact. Finally, with regards to the testing of the arithmetic Monte Carlo pricer, we wanted to introduce additional measures since it is what is the center of focus of this paper and of all of industry. So the additional test that we made was by comparing it to a very famous set of cases that formulate and constitute the benchmark for arithmetic options pricing. That is namely the paper by Vadim Linetsky that is being used by industry professionals and academics alike. It is considered to be the end of Asian options pricing. It's extremely accurate, and while the methods described therein are quite complicated in terms of a computational translation or the creation of some sort of pricer, just like the one that we made here, in order to price Asian options, it does provide us with a benchmark for other pricers that use other approximations, again, like this one. With those results specifically, again, we're satisfied. We achieved less than 1% errors in all of the different cases. And we attributed it to both the variance reduction techniques as well as the large sample sizes and the computational capabilities that were offered to us. And now I'm going to give it off to Snehal to discuss about some of the limitations of our models and our next steps.
Hi. So we could have added to reflect more accurately on price dynamics of Asian stocks, volatility surface feature to show more realistic result. We could test the pricing algo against real data, and you can see other pricing algorithms developed over the years. So these could have been some next steps. Below are some graphs which we have plotted. Yeah, so this is Asian put options, the Greeks for a range of underlying price and maturity. So similarly, here we have plotted put options against strike price, and could you please scroll down? Down. Yeah, so this is the implied volatility surface. Yeah, and we used Google Colab to run the Monte Carlo simulation. That's it. Any questions?
So this is the implied volatility surface for what asset?
So this is the implied volatility surface for, again, like SX5E. We got this example from a text from continuous time models. It's a course at Columbia University. It doesn't necessarily apply to our model because our model just assumes that volatility is constant across all directions. So in the case of this visualization here, the volatility in our model would just resemble a flat plane that sits at 30%.
In principle, you can also find the implied volatility surface of an Asian option. Mm-hmm. If you have options of many strikes and many maturities. So I thought maybe it's something like that. Yeah. So another question, have you used the Lévy approximation? Because in the beginning, you were discussing the Lévy approximation, the log normal approximation.
Yeah, so we incorporated that for these models here. We just made some comparisons between geometric average Monte Carlo simulations, just plain Monte Carlo, and then introducing it in geometric averages with the control variance reduction and specifically the log normal approximation. And we noticed that these came really close. So that, again, just gave us some more insights into what exactly, what are the benefits of using such an approximation and why it is not as just ludicrous as it first sounds to just assume that the arithmetic average is immediately log normal. we looked more into risk metrics, specifically JPM's risk metrics, to see exactly how log normal approximations work. And in this case, that's another graph that we tried to test. Something that you touched upon earlier is the floating strikes. And we decided to do that at a small scale so that we just test what a model like this could look like. So in this case, we have the different Greeks with 3 different strikes, 80, 95, 100, 105. And then like consequently all of the Greeks that we could calculate with it. And we just saw these different movements. But specifically with the floating strikes, we decided to look at the different surfaces for the value of the stock across strikes and across underlying prices and explore that for both put and call options.
Now that you have also a Monte Carlo implementation, you could also compare the Lévy approximation with the Monte Carlo simulation, because the Monte Carlo simulation doesn't make the log normal approximation. So you can see what's the impact of that approximation.
I see. Yeah, so just directly comparing the two and getting the difference in the same way that the variance reduction was, or the control variance was extracted.
Right, right, yeah.
That's really interesting.
Oh, very nice.